Is this thing on? Yeah, okay. All right, guys, so my recording software actually went a little haywire when I was trying to publish my video. So I already made it one time, but in this video, we're gonna go over your previous lesson, the free body diagrams, force practice, part 1. So I've kind of written down the gist of the information here from each problem. Got my calculator handy, so hopefully we got everything we need to get started. So in the first problem here, we're talking about the 75 kilogram bicyclist or cyclist, however you say that. They're pedaling, generating a force of 150 newtons. There's a 50 newton drag. And so we're asked to analyze the situation. We're going to draw a free body diagram, right? You can do this with the cyclist, but we know we can just use a dot. We're going to look at the number of forces, the net force, the acceleration, which will of course be due only to the net force, and what the speed is doing, if it's increasing, decreasing, or constant. So here's my cyclist, artistic representation, I know. So what we want to think about is, what are some of the forces? We know we've got a force due to gravity, which is equal to the mass times acceleration. We could think about that m times g, right? Maybe you didn't realize that the weight force, W, or as we're going to also call Fg, is simply the mass times gravity. So that would be 75 times 9.8, or 735 newtons. Now, what does that mean? That means now we can take that and determine that the normal force will be equal and opposite to that. We'll call that Fn, and that will also be 735 newtons, but in the opposite direction. Now, the bicyclist is not experiencing any changes in the state of motion vertically. They're staying on the ground, right? No wheelies, none of that. But they are pedaling to generate thrust or an applied force, and that's 150 newtons. And the way the picture is drawn in your on your screen, I think it was to the right. And then we also know now, hey, there's a 50 newton drag. So we're going to draw that back. Notice it's a little bit less, 50 newtons. So how many forces is that? 4. 4 forces. What is the net force? Well, the net force is, of course, what's left after all of these forces have fought. You're also going to see that as this little symbol here. This is sigma, and it means for us to sum all of the present forces. We actually only care about the x forces in this problem because the motion is horizontal, x is a horizontal variable, and that is going to be 100 newtons. How did I get that number? 150 minus 50. Now, we're going to take that number, and it's going to inform how we find our acceleration here. So we know that F is equal to ma. This is the net force that is going to be applied for this problem. So we know that's 100. And then we simply fill in the mass, which is 75, to help us solve for A. Divide by 75 on both sides, and we're going to get 1.33 meters per second squared. Pay attention to the units. That's a positive acceleration in that direction, meaning our speed is going to be increasing. I'm just checking to make sure we can see everything we need to see, and that looks good. Next problem. The next problem was the 7 kilogram rocket, generating 140 newtons of thrust, experiencing a 90 newton drag. So, again, in order to figure out what the number of forces is, we need to draw it. And yes, you should be drawing the arrows on the dot. So, here's our rocket. What do we know? The rocket's always going to be experiencing gravity. We're not in a vacuum. So, force due to gravity, again, that's mass times acceleration. I'm going to put mg here. So it's 7 times 9.8. So our force due to gravity, 68.6 newtons. Is there a normal force? No. We're not contacting any surfaces. But there's some other things happening. Okay? So we know that we're talking about 140 newtons of thrust. That will, of course, be in this direction. 140 newtons. Okay? That green doesn't work very well. No, it doesn't. But we're experiencing a 90 newton drag. What is the drag going to do? Well, as the rocket is moving upward, it's going to experience a drag pushing it back down. So we're actually going to add that down here. Notice that direction. That's another 90 newtons. So how many forces total? 1, 2, 3. 3 total forces. To find F net, the net force, we're going to have to figure out 140 newtons up in opposition to the total here, which is 158.6 newtons down. Right, that's a combination of these two. So my net force would be 158.6 minus the 140. That's going to give us 18.6 newtons, and it's going to be down. So the net force is actually down, even though the rocket is moving up, yes. Now, you can think about that. It's going to be moving upward, but the net force being applied downward is going to cause the acceleration in that direction. How do we get that? Of course, that's 18.6 equals the mass, which is 7 times A. Notice all I did there was write the net force, MA. F equals MA. That's the only formula we've got so far. And when we solve that, 18.6 divided by the 7 kilogram mass, we're going to get an acceleration of 2.65 meters per second squared. And that will be in the same direction as the applied or net force. Same direction as the net force. Therefore, if the rocket is moving up with an acceleration in the opposite direction, the speed will be decreasing. So, last question, and yes, most complicated, we have the elevator dude. Elevator dude, right? So the elevator dude, we can draw that. Yeah, that's the elevator dude. All right, so think about what we know. They told us this, they framed it a little bit different. They said a 630 Newton student. So what they actually told us was the force due to gravity is 630 newtons. But it's always helpful to know the mass of the entity that is involved here. So what we're going to do, we're going to set mg equal to 630. Make sure you can see that. Yeah, awesome. Okay. And then we know that G is, of course, 9.8. So the mass times 9.8 must have given us 630 newtons. So we'll divide by 9.8. And we're going to get that the mass of the student equals 64.2 kilograms. That's actually a question that we're going to be asked. I'll go ahead and fill that in. 64.2 kilograms. Okay? But we want to do that so that if we're asked about a question down the road, which you can see we are, okay? What are some of the other forces? So we know that the student is contacting a scale on the elevator, so there will be a contact force in the opposite direction, the normal force, Fn, and it is equal but opposite. So there's your 630 newtons. Great, that's 2. Anything else? Well, we have to conclude that because the elevator is moving down but accelerating up, right? How did we get that it's accelerating up the way the problem worded it? It said the elevator is moving down but it's slowing at 1 meter per second squared. So if it's moving down but it's slowing, that means the acceleration is opposite to the direction of motion. That's the 1. And so what we have here is an applied force. An applied force due to the elevator. So applied force. Notice that's going to be mass times gravity. Not mass times gravity, mass times acceleration. Not gravity in this case because this is an applied force. So that's another reason it was important to find the mass of the student. So we know that was 64.2 kilograms. And then the acceleration. Well, that's 1. How do we know that? They just gave it to us. They said it was 1. We just have to know it was in the opposite direction. So take a look at all of the forces here. Notice this is a sum of the forces in the y direction. Nothing's happening horizontally. And there are 3 total forces. So here's where it's going to get tricky. What's the net force? Well, if we drew our picture correctly, right, again, all we had to know was the gravitational force or weight, the normal force, which is equal and opposite of that, and then what must have been deducted as or deduced a applied force due to the elevator slowing down must mean an applied force in that direction, right? You're going to experience it pushing you up. Right, you feel that down here, but it's pushing you up so you can sense the applied force. then what's the net force? Well, the net force is just the applied force, which is 64.2 times the acceleration of 1, 64.2. What are the units? Newtons. Now, here's where it gets interesting. What is it that the scale is reading? Right? Because the scale is actually going to feel all of this. Or the scale is going to feel the normal force upward. That's actually what it's going to measure. Now think about that. As you go down an elevator and it starts to slow because you reach your floor, you feel your knees start to kind of buckle a little bit. So it feels like you're getting heavier. What is that going to do to the scale? Right, looking at, I have two choices, either the force due to gravity or the normal force for this problem. Right? If you're getting heavier, it's actually measuring greater than your weight. And so this has to be the normal force. But the other reason is that because the scale is below you, it's experiencing all of this in the opposite direction, right? Moving downward on the elevator pushes you down harder onto the scale, so it's feeling more than your body weight. Now, what does that amount to? Right? The amount that the scale is going to read is actually going to be this total normal force, 630 plus 64, 694.2 newtons. All right, guys, hope that helps. Good luck. I'll see you soon.